Hello, Professor Densmore, Samantha, and anyone else who's watching this video. My name is Yusuf. My teammates are Asbel, Christian, and Abdullah, who isn't here right now because he's doing some senior design stuff. And this is our EC311 final project, the game 2048. Before we go into the code, our distribution of this code is that Christian was all about the keyboard input, as well as implementing the board. Abdullah was the one who's essentially our glue guy. He made sure that all of our modules were working together, as well as did some debugging. Asvel's job was all about making sure the logic of the game works and helping out anyone else who needs help. And my job was all about doing stuff for the VGA, making sure the board output is right, as well as all the different colors for all the different blocks. So, Christian, let's begin talking about some code.
Right, so to start with, we'll start with the keyboard to BCD module. So in this module, we basically read the input from the keyboard using via the PS2 port on the FPGA board. And this input will then be encoded in BCD format, as you can see from line 43 to 47 there, which encodes for the movements left, right, up, down, and also the reset button. And then this encoding will be processed by the game and the board module. So we move on to the board module now. So in the board module, we have three main parts. The first one is the random number and block generator, which is using the LFSR or the linear feedback shift register. So this will basically generate the random values and random blocks on the game board. And then the next part is the finite state machine, where we have three states. The first state is the initial state, where we basically generate the initial values for each cells on the game board, which is just a value of 0. And then the next state is where we use the random values and random blocks, and then it will be placed on the board in this state. And then on the next state, or the last state, is where all the movements are implemented. So based on the keyboard inputs, it will be read by this module and then translated into movement. So yeah, so there's the move board left, and then there's like other parts of right, up, and down too. So next, Yusuf will explain about how we display this generated game board through the VGA output.
Okay, so now we're talking about the VGA output. We got to initialize everything about a typical VGA. We got to initialize all the red, the green, the blue, board color, all the pixel strobe, actually drawing the board as we can see near the top of the screen. Everything between 47 and 50 is using our other modules to go ahead and first of all create our display, have our clock divider, and make sure our VGA is 640 to 480 because that's how many pixels we're using. We're then assigning values for red, green, and blue. And then after that, we're going ahead and using the pixel strobe and essentially assigning all of our red, green, and blue values. We want our board to be cream white. So that's why we have the R, G as F and our B as E. Now, when we go to our board display, this is where we're actually drawing our board. As we can see our square board as well as our 4 different rows because we're having a 4x4 grid for our 2048. We're initializing everything up there, drawing in the assign statements where we have all of our different portions. And then after that, this is the one hot encoding we were talking about in our presentation that essentially we're going to go ahead and choose whichever one based on the most significant bit. So for example, the most significant bit is all the way at 4. We're going to choose row 4, 3, row 3, and so on and so forth. Now for the row, very similar because every single row has 4 different columns. So that's what we're doing between lines 42 and 53. This is just creating all of the columns. The next 3 lines, all the assigned statements are actually drawing them. And then afterwards, in this case statement, we have all of the different values and what colors they represent.
Right, so going from there, we have our overall game module, which is what implements this block diagram here, all this logic and everything and all its connections. This is where we're basically doing it. So we have our port, our VGA controller, our keyboard, a bunch of always statements that affect directions, given the keyboard input and a new value, and when the new value is pressed and whatnot. And that goes to the board, like Christian was saying. As you can see here, we're using display 7 sag and these LEDs, and that's really just for us to do some debugging as we're going along, just to see what values were being passed around and stuff like that. So we're here to help figure out some issues that we were having. So to go back to board real quick, there was one major issue that we had with board, which was the whole, it dealt with the clock and the non-blocking versus blocking assignments. So if we were to use blocking assignments, which allows us to do more sequential code or combinational code, that would cause a delay of about 300 nanoseconds, which then causes clocking issues. But then by using non-blocking statements like we have now, even though we have no errors in the video, there's logical errors because since things are all happening parallel, logic is being activated that we don't want to be activated, which starts to cause bugs. And these bugs can be seen by the player while we're playing the game. But we decided to embrace these bugs and actually make our game based off these bugs. So this is where we actually switched our game from being 2048 to what we like to call the Wild Wild West of 2048, which basically makes 2048 into a complete puzzle game where users have to press key whatever inputs in a very specific speed to be able to sync with the clock. And that allows them to actually get the first blocks into the screen after the first two have been placed and been combined. Because once they're combined, you'll have one individual block that will just continuously go around the board. And if the user can't sync with the speed of the clock or sync with the speed that they need to, no other blocks will appear. But if they are able to, they'll get a block, and then the game continues from there, where they start to being able to actually combine blocks, and blocks randomly appear. But the next issues that occur because of the bug is you start to get the glitching of blocks coming in and out because the board doesn't have the time to actually set all the values in it. And this causes the issue of actually seeing blocks come in and out. So you assume that you're about to actually combine blocks, but then you actually don't. Or you get the issue of invisible blocks showing up, which then creates the obstacle of the user not being able to actually combine blocks. So this just creates a very fun puzzle version of 2048, which is much more difficult, we would say, for the player. But it can be very fun to watch somebody play because it can be very rage-inducing. But if you have patience, it's also a very fun game just to play as a puzzle game because it really does become a puzzle game with these bugs. And instead of trying to fix the bugs completely, we decided to keep a couple of them in there just as a quirk of the game, to say the least, which allows the game to be its own thing instead of the traditional 2048.
And as Asbel said, this is a very family-friendly game, 2448 Wild West Edition. But as we're wrapping this up, we will now be moving on to the actual demonstration portion, where Asbel will go ahead and show videos of him playing the game. And yeah.
Guys, to the hardware portion of 2048 Wild West Edition. So as you guys can see, same project as we were talking before in the software portion. So first thing we're going to do is we're going to go ahead and program the device. So after that, you have what's your board, and over here's your FPGA with your VGA out and your keyboard in. Starting off, we have our 7-seg display, which really that's just used for debugging purposes, letting us know what states we're in and whatnot. And then throughout time, we'll have these lights blink on, and that's also for debugging purposes of telling us different input when different inputs are high or low, or different connections inside the actual system are high or low, since we can't visually see them. So that was our solution to help us debug while we were actually running on the actual board. So to move on to our game, so as we explained before, the way we display most of this is actually just using one base module called square. So this is a square, this is a square, this is a square, this is a square, which makes a whole row. and then we use that one row repeatedly 4 times to make the combination of all 4 rows. And then that's all put together on one big square, which is the actual board layout. And to get these crisscrosses, the way we did it was with the one hot encoding. So once our pixel reader gets to this point, it goes high, and it tells us that because this is above the board, to put this color. But once it goes low, it goes back to the board color, and that's how you get this pattern. Same thing going down. We did it cell wise in each row, and then we did it row wise in each row. So the row will go high whenever one of these are high, and then to be able to display it, you just put in your X, Y, color, and position. So to start off the game, we go ahead and press R. So when you press R, 2 blocks will appear randomly. The next thing you do is you can use your key arrows to move. So let's go ahead and move. You combine. As you can see, no other block actually came in. So what the user has to do is they actually have to play around with the game to actually be able to access the rest of the game. So yeah, there we go. As you can see, blocks do randomly change colors. So you see we have 2 greens now. We can combine them to make a red. And then if we keep on playing around, you can get another combination and another combination. As we explained earlier, this is really due to the bugs of, what is it called? Of the clock signal, the data not coming in on time if we use blocking information versus non-blocking. And one of our theories for that is it has to do with how big our multi-dimensional array is for the board, because it's a 4x4 array with 16 byte words in each cell. So that's a lot of information to be passing between cycles, and we think that's where we're getting an issue. But yeah, the user can keep on playing, and blocks will appear. And the more you play this game, the more it actually starts to a little bit bug out, to the point where blocks are hard to tell, because you do start getting multicolored blocks, and you got to figure out which one of those you can actually combine, to the point where some of them literally just become obstacles to stop you from combining blocks that you should be able to combine otherwise. So it brings a brand new challenge to the game that didn't exist back when we first started with 2048, which we think is very useful, because it actually gives a more entertaining edge to the game. But it can also be very frustrating because you don't know what's going to happen next in the game. You can either be here sitting around playing with the same 6 blocks forever, or if you go at the correct speed, other blocks will appear. But yeah, so the way you win, or there is no winning in this game. The only way to win is actually if you if you fill it up the whole box. So if it gets over flooded and there's even matches still, the game will be over. You can't continue playing. So it's really just a game of trying to be as patient as possible to see how long you can last in a very complex and challenging game. But yeah, that's it for our hardware portion. I hope you guys enjoyed. We did implement all the key features of 2048, from importing blocks to the 4-way directional movement, and to being able to combine blocks as we've shown in this video. The bugs just make it a more complex game, which we think is actually a lot more fun than the original 2048. So thank you.